Picking up from where we left off last time, we were looking at intermolecular forces, right? And we established that we had a couple of different categories. We have the dispersion forces, which are the transient dipoles, which are present in all substances. And then we have permanent dipole forces for molecules that actually are polar or have a dipole moment on a permanent basis, right? And we had said that as the forces get stronger, the boiling point of a substance should increase, right? That should make sense because saying the boiling point increases, that means it's harder to turn that liquid into a gas, right? What would make it be harder to turn a liquid into a gas? If the forces between the molecules are stronger, because to get to a gas phase, I have to have the molecules all separated from one another, right? Pulled apart so each molecule is traveling alone. If I'm looking at similar molecules, meaning things with similar geometries and what have you, then I should expect the boiling points to go up as the number of electrons goes up, which typically means that the molecule gets bigger or heavier, right? And that's because the dispersion forces get stronger in that case. So let's look at some actual boiling point data for some compounds, and this will lead us into our final sort of special category of intermolecular forces. This graph has it's got boiling point temperatures on the y-axis, and the x-axis is kind of divided up across sort of each line in the graph is going going down a column rather in the periodic table. Right? What do I mean by that? I mean, if I look on the bottom here is CH4, SiH4, germanium GeH4, tin SnH4, right? Those four elements that are bound to hydrogen in those compounds, those are in a column in the periodic table, right? So carbon's on top, then silicon, then germanium, then tin. And so as we go from the light end, which is carbon, because that's the top of the table, to the heavy end for tin, sure enough, the boiling point does steadily increase, right? That's kind of what we would expect. All of those compounds would have the same shape. They should all be tetrahedral, like the picture there for methane, right? Because all I'm doing is changing the row of the periodic table that the central atom comes from, but its valence electrons stay the same. In the other three plots, you'll notice something unexpected happens, and that's that on the left-hand side for the lightest members of each one, we have actually the highest boiling points. Those are ammonia, HF, hydrogen fluoride, and H2O or water, right? So those three substances over here, these all have anomalously high boiling points, right? And so in general, we would expect those boiling points to be the lowest in their respective lines, right? Think about what that would mean. If I took this line here that goes from H2Te, that's tellurium, Se is selenium, here's sulfur, those are the elements underneath oxygen in the periodic table. If I extrapolated that back, that would suggest that the boiling point of water might be closer to minus 100 degrees C than to 100 degrees C, right? And clearly that would be a much different world if that were the case, right? And so something different is going on there. What is happening there is those things are the result of what we call hydrogen bonding. That name is perhaps a little bit unfortunate, but we'll do our best here to explain kind of what hydrogen bonding is and when it's important, okay? Right now, just from those boiling points, we can see that this something is important, and it's going to be this thing we call hydrogen bonding in those cases for ammonia, NH3, hydrogen fluoride, HF, and for water, H2O. So what is hydrogen bonding? It's really just a special category of dipole-dipole interactions, right? Dipole-dipole says we've got a molecule that's got a permanent dipole moment, right? And the dipoles we want to line up. As intermolecular forces go, those are relatively strong because it's a permanent dipole instead of these transient dipoles, right? Hydrogen bonding is going to be a special subcategory of those dipolar interactions, and it's going to be even stronger than the others, okay? It's stronger than usual, mainly because a hydrogen atom is very peculiar, right? Because it's very small. It starts off with just one electron, right? So if that one electron gets drawn towards the opposite end of a bond, then that hydrogen is getting close to just being an exposed proton, right? So we can kind of get more positive charge on that end of things. When does hydrogen bonding take place? It takes place in molecules that have a hydrogen atom bound to, quote, a very electronegative atom, and in practice that means fluorine, oxygen, or nitrogen. Okay, if you think back to the previous slide, the molecules that seem to display this unusual strength of intermolecular forces were ammonia, that's NH3, so those are N to H bonds, HF, hydrogen fluoride, that's an HF bond, and water, H2O, that's H to O bonds, right? So those are the three elements with the highest electronegativities. Those are the ones that can get this to happen. So let's picture what would happen. Let's draw, I don't know, let's draw a water molecule. Oxygen is the electronegative side of the molecule, so I'm going to get positive charge showing up on my, that little delta thing just means a partial positive charge on there, and I'm going to get negative charge showing up on the oxygen side of the molecule, right? If I have that, then if another water molecule comes along, it's going to want to orient itself so that its oxygen with the negative charge will be near one of the hydrogens. Okay, so I'm going to set up this chain of things. There's a figure coming up in a moment that will draw that better than I can. Maybe it's easier if I do HF, right? Where this is the positive end, this is the minus end, right? If I have another HF nearby, it's going to want to orient itself like this, and so on, right? So they're going to be able to have interactions between these pieces here, right? This interaction where I drew the dotted line there, that's going to be much weaker than the interaction that is in a molecule, this one over here, but it's going to be stronger than most other intermolecular forces, okay? And so that's what leads to this, that's what we call this hydrogen bonding. Okay, it really is just another dipole-dipole interaction. It just happens to be stronger than most of the other dipolar interactions. Hydrogen bonds are especially important for water, and because water is important in the world and in life, hydrogen bonds are very important in biological systems and biochemistry. Okay, so just a couple words about that. Water has some really unusual properties as things go, and that graph kind of highlighted the fact that the boiling point for water is just almost ridiculously higher than one might guess based on other molecules, right? That high boiling point and the fact that it also has a high melting point, those are crucial for the existence of life as we know it, right? If the boiling point of water really was down near minus 100 degrees C, then the world would clearly be a very different place, right? Because assuming the prevailing temperature was similar, then the water that was about would all want to be in the gas phase. This is also important for properties of ice, right? The structure of ice is very, very open. There's a lot of empty space in it. And that actually means that the density of water goes up when it melts. That's a really unusual property, right? Water is peculiar in being a substance where its solid phase will float in its own liquid. Right? Most things, if you have the solid and the liquid mixed together, the solid will have the higher density, so it will sink to the bottom. Ice is obviously an exception to that, and that's really important for how things work in, say, in lakes and ponds when it gets cold out, right? That we get ice on the top rather than freezing from the bottom upwards. Hydrogen bonding is also really important in a lot of biological molecules, which we don't take up in this course, but things like proteins and DNA, where the complex structures where those get folded and wrapped around on themselves, a lot of the forces that hold those structures together, like the sort of famous double helix in DNA, that's actually held together largely by hydrogen bonding between the pieces on the different strands. That's what keeps them wrapped around one another in that structure, which kind of everyone is aware, at least, that that's the nature of a DNA molecule. Right? This is a picture I promised. So this is what a sort of view of a molecular scale of a piece of ice might look like. Okay, so let's pick out a water molecule. Let's pick out, I don't know, maybe that one there looks like a good one. Okay. So there's the red one is the oxygen, the white ones are the hydrogens, and you can see that the neighboring water molecules are all going to be oriented so that the hydrogen from a nearby molecule, like this hydrogen here, is going to be pointed towards the oxygen of the molecule that I drew the arrow by, right? Likewise, over here, I have another one where it's pointed there. The hydrogen from here is pointed towards the oxygen of the nearby water molecule. Okay, so I get this structure that sets itself up. And one thing you'll notice about this structure is there's a lot of open space in it, right? The molecules aren't just kind of getting smushed together. And so they're taking up a lot more volume than they might if they got into a less regular arrangement, right? If I just said, okay, just everything kind of put them together like they were just little, things that had that shape made out of wood or something like that, they could fit into a lot smaller volume. The fact that there is all that empty space in there, that reduces the density of the ice, and that is an explanation of why ice ends up floating in liquid water, which again is a peculiar property. Most things don't do that. This is, I think, a useful summary of a lot of the things that we've been talking about for a while now, right? Particularly, it's trying to compare intermolecular forces and intramolecular forces. The numbers that are on this slide in here, in that row, as it says down here, those are in kilojoules per mole, and obviously they're sort of ballpark numbers, they're ranges of things, right? But what do we see? We see, first of all, that the intermolecular forces, the things we're talking about now, those are on the weak side of things, right? Intramolecular forces, those are the actual bonds that hold molecules together, right? That join the atoms together. So if I think about water, the intermolecular forces are my hydrogen bonding that hold one water molecule to other water molecules. The intramolecular forces are the bonds that hold the two H's to the O inside of one water molecule, right? Intra is within, inter is between, right? And if we see this, we see that among my intermolecular forces, in general, the weakest ones are going to be the dispersion forces, followed by dipole-dipole forces, hydrogen bonding, which again is really kind of an extension of this category here, right? Because hydrogen bonding really is still a dipole-dipole force. It's just kind of the strongest extreme category of that. If I have things that are permanent actual ions, right? Like when I have an ionic solution where I've got, say, I don't know, chloride ions dissolved in water, or sodium ions and chloride ions in water, the forces between those ions and the water molecules are going to be very strong because the ion is a real charge, right? It's got more localized charge on it than something that's just a dipole. As it points out down here, if I go to an ideal gas, then my forces literally go to zero. Everything else has some degree of forces in there. Out here, I have covalent or ionic bonds. Notice that in general, those are much stronger, right? At least an order of magnitude or two stronger than the intermolecular forces, right? This is why when we boil something, we pull the molecules apart, but we don't actually break the bonds inside of a molecule, right? So boiling, there's enough energy at the high temperature to separate the molecules, overcome the intermolecular forces. There's not enough energy to overcome the intramolecular forces, right? When you boil water, the vapor rising up above there is water vapor. It's not a cloud of hydrogen and oxygen gases, okay? That's a nice summary of all the sort of magnitudes of things that both we've been talking about in chapter 7 and in this one little piece of chapter 8 that we take up. Going to finish with some things about materials, okay? A lot of people in this course will go on to take one or another of the various materials properties courses that exist on campus, largely in the College of Engineering. And so this is just a brief look at how some of the ideas of chemical bonding and intermolecular forces can influence the properties of materials. One really nice contrast is between graphite and diamonds, okay? Those are both forms of pure solid carbon, and in spite of that similarity, graphite is one of the softest materials known, and diamond is in fact the hardest naturally occurring material known, right? And so we can explain that by thinking about the bonding in those two substances, so let's try. Graphite has a structure that looks like this. So if I had a sheet of graphite, this is like looking down on top of it, okay? It's got this extensive network of hexagonal rings. There'd be a bunch of resonance structures for this, right? Like where, I don't know, start in this corner up here, where my picture has a double bond there. If I rotated that double bond one position in either direction, then all the double bonds would have to move around, right? So I'd get resonance structures that would describe this in a lot of different ways. That means those electrons that are in the pi bonds are fairly strongly delocalized. They're kind of running around in the plane of that sheet, okay? If I look at this structure, because these are all sp2 hybridized, right? And the sp2 hybrids mean around every atom I want to have a trigonal planar geometry, right? It should look like that. And to get the ring to be able to close up on itself, they all have to be in the same plane. And you can try and convince yourselves of that. But if I twist any one of those, then I won't be able to get it to wrap back around and end up at the same place, okay? So this entire sheet should be flat. It's locked in a plane because it has all those double bonds in there, those pi bonds, right? If I try to twist those bonds, it would break the pi bond because it would rotate those p orbitals relative to one another, right? So this is a flat layer of graphite. If I have just one of those flat layers of graphite, nowadays that has its own name. That's called graphene, which is a one atomic layer thick film of graphite. And people do lots of neat things with those. It has weird electrical properties. So folks are trying to make very small scale components out of it and other things like that. It turns out that within one of these planes, graphite actually is a pretty good conductor of electricity because the fact that those pi bonds can move around means the electrons in the double bonds, again, are pretty free to slide anywhere they want within that plane. Okay, and that's kind of what's exploited in some of these small-scale electronic devices that people make with this particular material. This is a contrast between diamond and graphite. So now we're looking from the side view, say, of the graphite, right? So this top piece here, this would be one layer like was in my other picture, right? And in those hexagons, I've got real chemical bonds. And so the carbons in there are about 141 picometers apart. That's the bond length of those carbon-carbon bonds in the hexagon, right? If I flip back for a second, in this structure, my carbon atoms all have 4 bonds right now, right? So I can't make any more bonds to any of those carbon atoms. And that means if I get this stack of layers here, the forces that hold the top layer to the middle layer to the bottom layer in this picture, those are intermolecular forces, right? Those are in fact just dispersion forces because I can't make any more actual chemical bonds, all right? Because those are weaker, the distance between those layers is much greater, right? It's about 335 picometers, right? So they're more than twice as far apart in between layers as they are atoms within one layer. What does this mean? It means that those layers can very easily slide across one another. That's why graphite is a soft material. It's easy to get it to deform. People use graphite as a solid state lubricant for places where you don't want oil vapor, for example. Some of you are probably familiar with that. This is how that process works, right? The lubrication, the ability to damp friction comes from the fact that it's so easy to slide those layers across one another because all I have to do is shift those intermolecular forces. On the right-hand side, there's a structure for diamond. In diamond, again, all the atoms are carbon, but now they're sp3 hybridized, right? And that means I get this network solid, right, where I get a tetrahedron around each and every one of them. And if you look at that structure, to break a piece off of that, we have to break a lot of chemical bonds. Right. These bonds, the bond length in there is about 154 picometers. It's a little bit longer than in the graphite. That's because of the resonance structures in graphite, where in diamond, those would all be single bonds if we just drew that structure, right? Because every carbon atom now has 4 bonds to it, right? But if I wanted to break that diamond, I'd have to break a bunch of those chemical bonds, right? And that's why it's really hard to cleave a diamond, right? That's why it is a very, very hard material. And because the bonds are localized there aren't these electrons that are free to slide around like in all those resonance structures. Diamond also happens to be the best electrical insulator that we know of because it's very difficult to get a current to flow through there because there are no electrons that are at liberty to move about. They're all stuck in their bonds there. Okay, and so the very dramatic difference between the properties of those two substances is very definitely reflected in the different ways the atoms are bound together at this sort of atomic scale is where we can see the differences. A little bit more here about forces between molecules. So we're going to talk a tiny bit about vapor pressure because it's a somewhat important property in a number of applications. We'll talk a little bit more about this right at the end of the semester when we're talking about equilibrium. But for now, we'll just do this as sort of an overview of things. Okay. So the intermolecular forces dictate the boiling points, right? That's what we've been saying throughout this video. The vapor pressure turns out to be the pressure that exists above the liquid if I put some liquid in a closed container, right? So if I took an empty flask, evacuated it, and somehow injected, say, just some water into it, right? I would end up with a system that has liquid in the bottom and has some amount of water vapor in the empty space above it, right? My system has to be closed, so the stoppers have to be in my flasks there. And this is the simplest to explain if we imagine that there's no other vapors in there. That's actually not important, but it's simpler to think about that way, okay? So if I compare two liquids here, right, if the red liquid here, when it says it's non-volatile, that means it's got strong intermolecular forces. It's harder to evaporate, right? The intermolecular forces are stronger. That means fewer molecules can climb out of the liquid phase, right? So over here, I have relatively little vapor, as evidenced by the sort of faint reddish color up above. Here, these are strong forces. Here I have weaker intermolecular forces. Right. With the weaker forces, more molecules at any given temperature, if these two liquids are at the same temperature, more molecules will be able to break free in the sample that has the weaker intermolecular forces. So over here, I get more molecules up in the vapor phase. That means the pressure up there should be higher, right? And what's happening is there's in both cases an equilibrium where the rate at which molecules evaporate from the liquid becomes equal to the rate at which molecules stick back into the liquid. The pressure above the liquid for the weaker forces will be higher, right? This vapor pressure, that's one way to categorize the forces that are present in a particular liquid. For water around room temperature, for example, the vapor pressure, I just happen to know this for some reason, is about 23 torr. It's not very much, right? Water is a little bit hard to evaporate. Its boiling point is pretty high, right? The normal boiling point, what we refer to as the boiling point, is just the temperature at which the vapor pressure becomes equal to 1 atmosphere, right? Because that's the temperature at which the liquid wants to all be able to evaporate, right? So at 100 degrees C, the vapor pressure for water is up to 1 atmosphere. Between the 23 torr at room temperature and the 100 degrees C, or 1 atmosphere at 100 degrees C, that vapor pressure actually sort of increases more or less exponentially, right? There are equations that model that, which we don't need to go into, right? But the fact that if I compare two liquids, the one that has a higher vapor pressure, that's another way of saying it has weaker forces between its molecules. Finally, in this video, we're going to take a quick look at phase diagrams, which is a topic that a lot of you will see in other places. There are some things in this course that I know people feel like, well, this is never going to come back anywhere else in my time in the university. For a lot of you, phase diagrams are definitely not in that list. And so these are simple phase diagrams, because what I've got on this slide and the next one are a couple examples of phase diagrams for a pure substance. This one happens to be water. Okay, so what is a phase diagram? It's just a visual representation of what is the stable state of something as a function of temperature and pressure, right? So temperature's on my x-axis down here, pressure on the y-axis. If I start off, here is a 1 atmosphere pressure line, right? So if I go across that dashed line, that just tells us things we know. Right? It says that temperatures below 0 degrees C, my water should want to be a solid, should want to be ice. Right? Between 0 degrees C and 100 degrees C, it should want to be a liquid. So it's in the blue part there, right? If I go above 100 degrees C, that's point C, then I get over here, and then my water should want to be in the vapor phase. Okay, that's all stuff we know. If we look in other places here, we can see some different things, right? We can see an interesting point down here. This point labeled A, this is the so-called triple point, meaning at that particular combination of temperature and pressure, just a hair above 0 degrees C and about 4.5 torr there, we get the triple point of water, which is a point where we have the curious combination of all three phases being able to coexist at the same time. If you picture that, that means you would have a sample of liquid water that had ice in it and was boiling all at the same time. That's really hard to imagine, but that's what would be happening there at that triple point, okay? If I come up here, this is another interesting point. This is the so-called critical point. Above that point or beyond that point, if I come further out here, there is no longer a way to distinguish between a liquid phase and a vapor phase. They coalesce into what is referred to as a supercritical phase out there. And then other places we can see just where there'd be equilibrium between, say, this is the liquid vapor equilibrium line, this one here. So that really is the vapor pressure curve, right? That says if I come down here at this 0.009 degrees at the triple point, my vapor pressure is 4.58 torr. At 100 degrees, it's up to 1 atmosphere, and it varies in between like that, okay? I'll take one more slide here and show a comparison. The left-hand panel is still water, the same picture that was on the previous slide. The right-hand panel is CO2, carbon dioxide. You can see a couple things. One thing you'll notice, perhaps, is if you look at the solid liquid line, you will see that over there for water, sorry, my computer is doing weird things here, but I think it's going to be okay. If I look at water, I have the case that line is sloping to the, it's got a negative slope. It's the simplest way to say this. I'm stumbling with words now as I look at that line, right? On the CO2 graph, my solid liquid line now has a positive slope, right? That actually reflects the fact that for water, the solid is less dense than the liquid, meaning that ice floats in liquid water. The positive slope over here, this one reflects the fact that solid CO2 would not float in liquid CO2, okay? You can see that, at normal pressure, at atmospheric pressure, I go from solid CO2 straight to gas phase CO2, right? To get the liquid to exist, this is the liquid phase, I have to be above 5 atmospheres of pressure. Right? That's actually why people refer to solid CO2 as dry ice, because it doesn't melt, it doesn't form a liquid, right? It just evaporates, which means it's kind of a little bit tidier than water ice for chilling things. It's also colder, right? If you come up here, this is the critical point for CO2. That one's kind of interesting just because the phase beyond there, that supercritical state for CO2, has actually got some applications. Among other things, people use CO2 beyond the critical point. That's one of the ways to decaffeinate coffee. If you take coffee beans and just soak them in that supercritical phase of CO2, it turns out that will dissolve caffeine out of the beans. And then you pump that away and it leaves you with decaffeinated coffee. And so that's an actual application of this somewhat peculiar state of matter that exists out there. You can see CO2 also has a triple point. In this case, it's at 5 atmospheres and minus 56.5 degrees C, give or take, right? But that's a feature that phase diagrams generally have. In a materials properties course, a lot of you will see phase diagrams for things that are not pure substances like this, things that are mixtures or solutions. Alloys, a lot of them have really complicated phase diagrams, and so many of you have that to look forward to in a future class, depending on which actual field you venture into.